So here we go. Applications of electric field. So as we go, like I said, electric fields take some time to think about. But they can be a little weird. All right. So here, this is kind of like a review question to start off with. It says we have two parallel plates. They have equal magnitude but opposite sign, which is what you should expect for two parallel plates. What change would be made to increase the field strength between the plates? Okay. So it gives us these options: increase the magnitude of charge, decrease the magnitude of charge, increase the distance between the plates, decrease the distance between the plates, or increase the area of the plates while keeping the magnitude of the charges the same. Tell me what y'all think. I'll give out the access code here in a little bit. Um, okay. So first of all, if we go back to the equation that I gave y'all for, you know, was that electric field strength between the plates? I don't know what you said. E equals what? You don't remember? Okay, so epsilon naught's a constant. Again, Q over A is our charge density. So first of all, is D in there? No. So C and D can't be helpful. Because if this, first of all, this only works if D is very small. And so if it's very small, it doesn't really matter the distance, as long as it's much smaller than the area. So that's not going to be helpful to change the distance, because obviously increasing the distance will decrease your field at some point, which we don't want in this case. So increasing the magnitude works. Right. More Q, more E, right? Obviously decreasing wouldn't work. And then the last one says increase the area. Well, bigger area usually smaller. Right? So if it's a decreased area, cool. That one's not. All right? So this is kind of a looking at that formula. So if you weren't thinking about that formula, then that makes sense. That's a good one. Two plates of parallel plate capacitor have these charges, equal and opposite, placed on them, leading to a uniform electric field between the plates. The distance between the plates is then doubled. The electric field, C. Yeah, it's the same one, yeah. So, let's write it again real quick. So again, it's E, Q over epsilon naught A. And epsilon naught is that 8.85 times 10 to the negative 12. So that's so that doesn't change. And again, we're assuming that the D is still pretty dang small compared to the area, so even if you double a really small number, it's still going to be pretty small. All right. So like I said, at some point, yes, D will cause that formula to break if you just make it too big. But, like I said, it should be much, much smaller than it to begin with. All right. Electric field of a point charge. So this is kind of what I mentioned last class, that if you just have 1 point charge, it's essentially Coulomb's law without two Q's in it, with just the one Q. So we talked through a bit of that last time, so I'm not going to do much more than that. So then, essentially, how you would find this in real life is you put a set charge there, and then you probe it with a second charge to find the force, and then you go backwards and you find the E. So if we can measure the force of the second charge and the size of the charge, we can calculate the electric field. So, like I said, we pretty much talked about that last time. So I got a little ahead of myself, but yeah. All right. So any questions about this? We covered that. So there's an electron in a hydrogen atom orbits the proton at a radius of 0.053 nanometers. What is the electric field due to the proton at the position of the electron? So, we draw this here. We go, okay, got ourselves a hydrogen atom, a little proton electron wants to stay near that proton. Right? So, you know, I know you can't really think of electrons and protons like this, but if you think about them classically, like just particles, if you think about the thing having such a strong electric field, well, it's going to have a huge force on it, right? But, I mean, the force isn't going to be too big, because essentially you're just going to multiply by 1.6 times 10 to the negative 19, so that's still going to be pretty small, but again, your electron is got like no mass. And so if you calculate the acceleration, it gives you a really big acceleration for that tiny mass. But also remember, the electron's going to be moving pretty fast. And so it kind of makes sense, like I said, you shouldn't really think of it classically, but I think it still makes sense that like if this thing's got a huge acceleration, you know, pulling towards the proton, but it's got this huge velocity, it's going to be trying to keep up, but it's just going crazy. Like I said, you shouldn't really think of it like that, but is everybody okay with this? And hopefully I made these calculations correct. Number 4, what are the strength and direction of the electric field as indicated by the dot? Specify the direction as an angle above or below the horizontal. So, strength and direction, so you've got to calculate it. So this is actually similar to the example we went over this morning. You have to do you have to find the electric field here. So this guy is going to have an electric field pointing this way, right? That. And this guy is going to have an electric field pointing that way. And so you have to add vectors. Yay. It's a little bit easier because we only have an angle on one of them. But it gives us, you know, this is 5, this is 10. So we can find this angle here. All right. Do you want me to go through all of this? Okay. So, well, we start with our electric field calculation. I guess I'll stick to red and blue here. Well, not red. So for the top one, we just do a E equals K, so it'll be 9 times 10 to the 9th, right? Times the charge, so in this case the charge is 1 nanocoulomb, so it'd be 1 e to the negative 9th. Well, that's convenient, isn't it? Over the distance between them, so in this case the distance is 5 centimeters, so that would be 0.05 meters, right? Squared. Okay, so on top you have 1 divided by 0.05 squared. So what do y'all get here for this electric field? 3,600. This would be newtons per coulomb. Right. Which you can prove if you actually cut up the units. Everybody okay with that? That's just the electric field from the first charge at that point. Alright. Was it? Would it be 9 or 10? Oh, yes, it would be 9. Did you use 9 or what? I can't tell. Because this is 9 times 1, which would be 9. Huh? Yeah. Okay. So yeah, it would be 9. I did say 1. Because 9 times 1 is 9. Alright, so let's do the next one here. So let's do the other dot. So we should get an electric field for that point as well. So I guess I do it over here. So it's still 9 e to the 9th times, what's this charge? Negative 1, which we don't put the negative in, that's direction. So we still do 1 e to the negative 9th, which again kind of cancels, so it's 9. But the distance, in this case, what's the distance? It's not 1 and it's not 10. Not right, either. Yeah, Pythagorean theorem, something. I'm going to write it as time squared plus 10 squared. What does it come out to be? 8.66. Okay. So what do you get for this force here? Or not force, electric field? should be smaller than that one, because it's further away, but the same size, you know? Newton's first law. I believe all of this is in the demo, but you know, it's better to talk through it. Okay, so we have our two electric fields, so now we have to do vectors. So now to add vectors here, you want to break them into their x and y components. For the first one here, it's already in its x, right? There is no y. So there's nothing to break apart for the first one. So this one's already done. But this guy here, the blue one, we're going to have to do some math. So mathematically, geometrically, however you want to say it, this angle here is the same as that angle there, right? So we know this is 5, 10. Wait. So you got 8.4. Yeah, that's the x angle.
I got 11.4.
Is that where you got the 720? 720 sounds right. Okay, well that's fine. Yeah, it should definitely not be 8. So 11.2, that sounds more correct. All right, so now, to find this angle here, we can do whatever you want. I would just use these two, they're nice numbers, so that would be a tangent, opposite over adjacent. So I do tangent inverse of opposite 10 over 5. What do you get for this angle here? Okay, and so that would be the same as this angle, so now we can use that to break it into an x part, right? And a y part. So for the x, we use cosine, y for the sine. So, let me get down here. So for x, I'm going to say, what's our force? So 720 times the cosine of 63.43. And then for the y, we do 720 times the sine of 63.43. All right. So the y, what do y'all get for the x and the y?
You have 322.
322. 0.05. And then what do you get for the y?
642.
What did you say?
643.96.
43, 6. Okay, cool. So now we add them together like vectors. So the y, there's nothing there to add. But for the x, we get, what, 322.05 plus this 3600 here. So I'll write in yellow for our vector addition here. So it's 3600 plus the 322. What do you get? 0.05 or something? Oh, that's all right, just that's all. Okay, so that's our x, right? Y is the 600. So now to find the strength, we do the Pythagorean theorem. So for my total electric field here, it's going to be square root of 3922 squared plus 643 times whatever it is. So if you think about these two vectors that we're adding together, so we have an x going like this, and then we have a y going up, right? So opposite would be the y, adjacent would be the x. So we will do 643.96 over the 39.2. Gives an angle of something.
9.3.
9.3. That's it. Now, I will point out a couple of things. Well, first of all, are there any questions? So, we have a small angle because, well, the y isn't very big compared to the x. And it didn't have much of an impact on our total here. I do want to point out that a lot of problems that you get are going to be more one-dimensional stuff instead of two-dimensional. Because again, two-dimensional to me is more about vectors than it is about actual electrostatic calculations. But just be glad they're not three-dimensional. Not quite the real life, but real life would be literally the same thing, just all of this, you just have to do it again. Which nobody wants. Okay, so we don't go quite realistic here, but hopefully. What have I,
We did kind of like that.
did I mess up there?
Yeah.
Or I messed up here?
We did think this thing like kind of like that. I'll do all of that.
I mean, it should give us a different angle, which is fine. Oh my gosh. Okay, no, okay, so hang on. Oh yeah. First of all, yes, in this write-up, I used a different angle, literally changes nothing. Just in the write-up, I found a different angle than what we did on the board. So first of all, that doesn't change anything. That's not why it's wrong. Now why it's wrong. What did we screw? It's erased now, so you can't see it, but here, I'll give you, I'll write back the mistake.
Did you see the difference in sound wave?
I wrote this, right, start off with,
Yeah.
that's wrong.
Oh.
Wait,
It's
what?
It's a negative sign.
Oh.
So the x's should be there. Okay, so everything we did right, I just wrote that wrong and then just let everyone know that.
We should do
But that's why we end up subtracting here, because remember, we got that like 643.96 or whatever, so that's the same number, that's fine. But we end up subtracting it because it's going in the negative direction. The y, yeah, so x and y are both negative, so they're going that way. So the x's end up subtracting, and so our angle ends up being, well, basically the opposite of what we did. Because it's going down. So, does that make sense? Oh, there we go. It's one of the reasons why I write this stuff down. Okay. Again, this is why I don't like assigning these problems, but here we are. I said I don't like assigning them, but I have to, because that's what they expect you guys to do. So, because to me, again, this is more about the vectors here than anything. Okay. Which of the two sets of electric field vectors is possible? A is possible, B is possible, both are possible, neither is possible. I did mention this in the notes last time. demonstrations, we did some of these already, we'll do some more. Ranking order from largest to smallest, the magnitude of the electric field, the black dot. So we had a similar problem like this when we were doing the courses. This is just electric field, so you don't need two charges. So we're just looking at the electric field at the dot. So what do y'all think?
Maybe three is probably the largest. Maybe two. The distance doesn't matter this way.
This is dozen. You're thinking of capacity, not a capacity.
Wait, this one you use the,
Just the E, K, Q,
it's not the
Or
Q
R
or
squared.
epsilon naught?
no, it's only for capacity. It's electric field and a capacity. It doesn't matter with distance because you have essentially charges on both sides,
Okay.
inside the capacitor.
Okay.
But that does not work out so. Okay. So all charges, oh yeah, this is a confusing question. All charges have equal magnitudes, in cases 1 through 4, as shown. Is the electric field on the dot to the left, right, or 0? So these are your answer choices, A, B, C, D. These are the problems. So what you have to do is you look at problem 1, and you'll tell me, is the electric field here to the left, right, or 0? Well, at the dot, because the electric field from a positive charge does what? Goes away from the positive, so this goes out, right? The positive, and I'm not gonna draw this for all of them, but goes out in all directions, right? So the negative does what? Goes in, so are those 0? Well, they will do some canceling, but will it be 0? No, because which one's stronger, the negative or the positive? The negative is stronger because it's closer to the dot. So this one has a field to the right or the left? Left. So left for number 1. Okay, so now number 2. Has to be B, so 2 should be to the right, right? So let's see. So the negative charge of the field go in or out? In, right? Positive goes out, which one's bigger? Positive, so this should be to the right, right? So 3, does this field go in or out? Out. This one in or out? Out, so that has to be to the left. What about this one? So this one goes in or out? In. What about this one? Which one's bigger? Inside. This one's bigger.
Wow.
Does that make sense? So these kind of problems to get you ready for the bigger ones, we gotta do all those calculations, so hopefully you don't screw up your direction and spend 20 minutes doing nothing, right? There's more. All charges have equal magnitude rank in order from largest to smallest magnitude of electric field. So, that's basically what we just did. So here, 1, the field goes to the right, and then the negative also goes to the right, so these two add, because they're close. These two subtract, but the positive is further, so this thing ends up subtracting and going to the left, so that one's definitely smaller. 3 adds, but again, it kind of adds like these two subtract. So 3, is going to be bigger than 2, but not as big as 1. This guy's way up here. And then the last one should be 0. So the magnitude and direction of the electric field at point A.
Yes.
Is that your answer?
Good question.
All right, so, well, we can work through this, hope I won't make mistakes. So determine the magnitude and direction of the electric field at point A. Okay, so, we got point A right here. Y'all wanna work through this, or just look at it? Look at this. So first off, let's look at these fields. So positive is gonna put a positive field here, right? This one is gonna attract or repel us. Repel, that goes out. And then this guy attract or repel. That's right. Yes. Just wait till you get bored. Like I said, this triangle seemed real bad until you get to a square and they're like, wait.
Okay, how do we know that, like, A is positive, that's positive? Because it's,
No, we don't know. We don't know. It has no charge.
oh, okay.
So you just think about like the field comes out from this guy, the field comes out from this guy, and it goes into that. And these are definitely not drawn to scale. I just drew the directions. But we screwed that up, or I screwed that up. Okay, so we got that. So now we go, okay, well, let's calculate the electric field. So, whatever, I guess we'll start here. Talk about it tomorrow. So the electric field is going to be K, 9 times 10 to the minute, times charge. So we're looking at this point right here. I'll just say 1, 2, 3. Make sure we know what we're talking about. So at point 1, this is 10 nanocoulombs, so 10 e to the negative 9 over the distance. What's that distance? So 2 centimeters is 0.02 meters, okay? That'll give us a number. I'll call it E1. Then E2 is going to be 9 times 10 to the 9th times a negative 10, but we don't plug the negative in there, so 10 e to the negative 9 over a distance. Like I said, I'm just going to say square root of 1 squared is 2 squared. Whatever, that number. And then the third one, I mean 9 e to the 9th times 5 e to the negative 9th over, that was 1 centimeter, oh, 1 squared. 0.01 squared. Actually, I don't even need to write the square root because I ended up squaring it. So. Thinking about that, that should be 0.01 squared plus 0.02 squared. Taking into account. Okay, so do y'all have any numbers? So this should be 10 divided by 0.02 squared. 90 divided by 0.02
Okay.
squared.
Are you, there E2 or you square root now?
Well, I was square rooting it, but then you also have to square it. So I just can't do it. Because this is square. I mean, if it makes y'all feel
Oh,
better.
that's right, okay.
Okay.
What was the first one is, right, okay, that's how it is.
That's what I got. If somebody else has a different answer, we'll see. So the second one, you still have 90 on top, divided by this, whatever the actual distance is. All right. What do you get for the third? Which makes sense. It's further away, so it should be less. be bigger than the things we dealt with before, because these are bigger charts. 450,000. Now this one seems to give us the biggest number, does that make sense? Well, it's definitely the closest, and it's not quite as big as the other two, but the distance really matters, right? Okay, so, there we go. Those are our magnitudes. So now to add them together, we have to do a little geometry. Now luckily, even though we have three charges, this one is an X, this one is a down Y, so we only have to split this one guy apart, right? This is the rectangle. So let's not forget this direction here, so we need to find this angle, or we can find this angle, or we can find this angle, whatever you all want. What angle do you all want to find?
That one is just fine.
Seems just fine, okay. So, if this is our triangle, this whole thing, right? So finding this angle here, this side would be 1, this side would be 2. We need to find that angle, so do tangent inverse. Opposite, in this case, 1 over 2. Right? It's tangent of a half. Inverse tangent. It's 50, right? Okay. So 26 degrees. Everybody must be okay with that? Don't hear any objections. Okay, so now we need to break this guy into its vector components, right? So, to emphasize this, I'm going to draw a little triangle. And we've got an X component and a Y component. And our angle is theta there. So the X would be sine or cosine?
Cosine.
Cosine. The cosine, so this is what? 180,000. Cosine of our angle, which is going to be 26.6. If it's a number, and the Y will be 180,000 sine of 26.6. We all get it. We're 7. And then we all get to the Y. Just 80,000. 6. Okay, cool. 5. Okay. So now we add vectors. So we have to be careful about the direction here. So for our x's, we'll have one x going this way, but the other x is going the opposite direction. So we're going to have to subtract those two. So for our electric field in the x direction, we're going to do the x, which was 160. Let's start with the positive one. So that's E1, so that's 225,000 minus the 169, whatever. 947. Why is that fun? Zero 5 3?
Yes.
Okay. And then the y is, well, we have the x, sorry, not x. We're looking at the y. We have this guy going down, so we call that negative. And then we have this guy going up, and we call that positive, so it's up to 80,596 minus our 450,000 0, and so we should get a big negative number of how much?
99,444.
point, we do a squared plus b squared equals c squared with these two guys, this guy and this guy. Define our magnitude, and then do inverse tangent of opposite over adjacent. So in this case, opposite, you know, we're gonna end up obviously mostly down here, but also, oh, positive, right, a little this way. So that if you're looking, say, for this, I'll probably try to understand it. Whatever, it's opposite over adjacent. I don't want to say it wrong here in the last few seconds without thinking. So all that should be here. So, looks like we're on the right path, right? And then there it is. So that's basically what we got. Put in the notes that. So I'll go ahead and email out the password to the quiz. Go ahead, and you don't have to do it today, but if you do it sometime, it does have a close date on it. So, sticking with the close dates of the school district, essentially, if you're taking that today, if you don't take it today, then, I guess it's Thursday, like if you took it on Friday, that would be considered like a makeup day. So I give you 4 school days, so Friday, Monday, Tuesday, Wednesday. So you have until Wednesday at midnight today.
And then the part, explanation.
Sorry, I'm So it's not, it's not something that we learned in school. I find that you because the thing is like, for everything you do in here, I have to do this. But like in physics, you have so like this would be like your head. So there's no get over my level. I like to use, and so if you say, okay, this is going in the right direction, this is going wider, you don't have to calculate this to do that. So I wish you did that in here. You don't. And I agree.
Like a quiz every, I know.
Yeah, it's just not a thing that is supposed to be taught or learned. And so like I could teach that, but the problem is like the AP test expects this.
Don't do that on me.
Yeah, you can do it for the you can, if it's a free response time, they'll understand it. But like, you know, as far as multiple choice or whatever, they're gonna give you like multiple choices like this. But yeah, as far as free response, like if you get, like when we get the free response in here, you can do that to me, I'll have to take a second and go, oh, right. But, no, that's fine, it's just not an objective for this class, which sucks. Because I think it's something that just comes along with calculus.
Yeah.
I don't remember where I learned it, but I know that in physics, we just started using it one day, I was like, wait, what? Because it doesn't make a whole lot of sense until you really understand it, and then it's like, oh, God, why are we doing all of this?
Yeah.
Because, yeah, it's a pain in the butt, and I don't like it. But yes, if you do it on the free response or whatever, it'll be fine. Because remember, the free responses are graded by people, and honestly, if a physics 2 teacher doesn't understand that, then they're gonna ask you about it. Like they're gonna be like, I don't know what's going on here. Because the way they grade it, or used to grade it, I don't know how they grade it now, probably different, but the way they used to do it is literally they would just have like one big long table. And like you'd have the head grader at the table and you'd have everybody else. And the head grader would like hand out the problems for everybody to grade. And so every problem gets graded twice. So I'm thinking about me, but also I have to think about like the other physics teachers in the district. Not that any of us have been AP graders in physics, but the whole point is like if you're at that spot and you don't know what's going on, there should be other people. So I feel like even if you did that digitally, you can still have a bunch of people around and be like, hey, what is this?
I feel like that should be easier.
and making it, you know, and lowering the level. But I used to be really bad at that.
Okay, so, okay.
So yeah, if you do it with unit vectors, that's fine with me, I don't care. But just remember that, like, their problems in here, like the multiple choice ones are definitely gonna be expecting stuff like this.
Yeah, okay.
Because I feel like we, you know, it's not like they can't learn it, but I think most of them have no idea, and I don't know if I have the time to explain all of that. All right, well, it's all right.